is Voigt, and I'm based at the University of Glasgow.
Hello, I'm Matthew Daws and I'm based at the University of Lancaster.
Hi, I'm Adam Skalski. I work in Warsaw in the Institute of Mathematics of the Polish Academy of Sciences.
Our program brings together three different groups of researchers in different fields. So as in the title, so we have quantum information, quantum groups, and operator algebras. And all these are related to quantum theory in one way or another. Operator algebras is the study of algebras of bounded operators on Hilbert space, C-star algebras, von Neumann algebras, and that originated from the study of observables in quantum mechanics, but has evolved into a mathematical field in itself. Quantum groups started in the 1980s with the study of quantum integrable systems, and roughly speaking, quantum symmetry, the study of symmetries in quantum systems, and perhaps the youngest of the three subjects is quantum information, which is roughly speaking about the study of information processing using quantum resources.
So one thing that sort of links all three of our topics together is the study of quantum correlations, which started with Bell's inequality and trying to explore whether quantum mechanics really is different from classical mechanics or whether there's some sort of hidden statistical theory behind. And Bell's inequality said no, there is something special about quantum mechanics. And then there's been this subsequent, for a long time, study of can we really pin down how much benefit or advantage does quantum mechanical systems give you. So this led to some conjectures about whether these different correlation sets were the same or not. And it was eventually realized that there's actually deep links with operator algebras and the so-called Kohn embedding problem. It's very surprising that these should somehow be the same. And then recently, the original the sort of quantum correlation has been refuted. There's been a counterexample coming from computer science and using ideas around Turing machines and somehow encoding a Turing machine into this quantum mechanical setup, which gives this counterexample to this problem in operator algebras. At the same time, there's been a lot of study of sort of these non-local games, which give you an operational way to get a handle on these correlations. And in particular, games coming from graph theory. So you sort of set up a game that a verifier tries to interrogate the players whether they have a homomorphism between graphs or not. And it turns out that if the players can use some quantum resource, they can convince the verifier they do have a homomorphism, even when the graphs aren't actually homomorphic. And then links between this and quantum group theory, the study of quantum sort of automorphisms between graphs was revealed. And so these three areas of operator algebras, quantum information theory and quantum groups are hence linked by these things. And our program has been exploring lots of things, but we've been particularly focusing on this area.
So as our program gathers people who come from very different research communities, so one challenge that we identified and actually was mentioned by many participants even prior to the program is the different languages that these communities use. And I will give a very concrete example. So there are graphical calculi, which are effectively a diagrammatic approach to the study of tensor algebra, tensor categorical computations, which is very, very common for people doing quantum computing, for example. And it's fair to say it's somewhat alien to, say, hardcore operator algebraists. And there was a lot of interest of trying to understand how we can bridge this gap. So one thing we did, we organized a series of discussions, lectures, presentations, notably by people from Oxford and Edinburgh who came and gave lectures, presentations, and there was a discussion of how you can use it. And we hope that this is a very concrete example how this language gap can be at least made narrower. So I'm not sure that whether we will all use diagrams in our work from now on, but hopefully we'll feel less stressed and less lost when we see them in the work of other people.
During our conference this week, we've heard about very interesting new developments, and that ties in with our program. So just to mention work by Slofstra on undecidability results, regarding positivity in certain operator algebras. There is work involving the MPA hierarchy and relating this to a work of Manchinska-Robertson on quantum isomorphisms of graphs. And maybe, a third theme which has been quite prominent throughout the program and also here at the workshop is quantum graphs. So that's a relatively new concept which has really evolved a lot, and there is now really interesting results, applications, further potential for this to be developed, and that's perhaps some of the things that we have seen in this program.
So I suppose two things that applications. We had an Open for Business Day where we had some people from industry, quantum computing startups. Perhaps I shouldn't call them startups anymore. It seems quite an established field. People from government who are interested in sort of quantum supremacy, when or if quantum computers get powerful enough to break cryptographic systems. We're going to have to put something in place. Ideally, we're going to have to put something in place early. And to me as a mathematician, it was really exciting to see people in business talking a language I understood and really doing research, but that has actual applications to building quantum hardware. A second interesting topic was talking to physicists during our program and seeing talks by people studying quantum statistics. So big thing about quantum mechanics is measurement. It's really, really difficult. That's central to how quantum physics works. So how can you learn information about a quantum experiment? There's a new type of statistics required. And it was interesting to see some of the maths I know being used there. And also people doing sort of rigorous physics, which again is something I hadn't seen before, but really sort of making ideas from physics really rigorous using some of the mathematical tools that we've been exploring.
The very nature of our program was built on joining communities of researchers working on the topics that I would say 10, 15 years ago seemed completely disjoint. Now they're not disjoint anymore, and it's not only inside mathematics. So during the program we had visitors from the physics group here in Cambridge. One of our participants gave a talk also in the department here in the Center for Quantum Information, which is a kind of effectively a computer science group. So I think that in short the answer is yes. There have been many examples of this cross-fertilization between different fields of mathematics, mathematical physics and computer science.
Well, in terms of organising, it's been incredibly easy because of the support we've had. Almost all of the local issues have just been dealt with transparently, and that's been really, really nice that we can concentrate on just talking to people.
Right. And in terms of just experience of being here, so I can just add something really personal. So I work in Poland. I originally come from Poland, but I was a PhD student and a postdoc in England. And it's wonderful to be back again for a longer period. I visited INI before, and I always come here with a lot of joy. And the chance to stay here for several weeks, this is absolutely great for personal, social, scientific reasons, all possible ways.
I can only agree to that, and maybe just to add that we've also had very positive feedback from the participants. So they told us that they really enjoyed this program and loved the environment here. So I think it's really a very good environment to be productive, focus on the research, and all the other stuff being taken care of. So that's great.
So maybe just one concrete thing that I would like to add in terms of what happens next. So as Matt was saying, this is a very timely program, and we see the evidence of this in the following fact. So during the workshop, we heard speakers announce, for example, a big annual series of conferences which will precisely connect quantum information and operator algebras. They will start next year. The first one will happen in Canada. The second one will happen in 2026 in Stockholm. So you see that this is somehow, there is a natural need in the community. So we also heard about several smaller workshops. We are very happy to see it. This is the right time to come here.